Hello guys, so let's continue. This is lecture 10.2 and we continue talking about dual spaces. So duality. Okay, so here is a fun question. So we know that, let's suppose that V is a finitely dimensional vector space. So then V star dual space is isomorphic to V dual, but this map is not canonical. So not canonically. What it means? It means that there is no simple formula I can write which will take a vector V to some map from V to F. Okay, so then one can look at the dual space to the dual space. So this is something really messy. So element here. So this element here, elements here are maps which take a map from V to F, and to every map from V to F they assign some element of F. So they take an element which is a linear map from V to F, which is an element of V star, and send it to F. So these gadgets, of course, they form this dual space to the dual space, and since we know the dual space is isomorphic to V, this is isomorphic to V star, which is isomorphic to V. And of course it sounds like completely the same story, but the fact is that actually there is a very natural way to think about elements of V star as elements of V. So though V and V star are isomorphic not canonically, you need to choose a basis. There is a very simple way to write down a map from V to V star star, which will be an isomorphism. So claim or theorem. So the main theorem of this part is that there exists a map which I will call D for duality from V star to V. Sorry, from V to V star. So what this map does, so this map takes a vector V, so D of V inside V star is a map which takes every functional alpha in V star and plugs in V. So this is D of V. So again, I take a vector in V, and then I need a functional on V star. And this is how it works. Take any element of V star and plug in this fixed vector V and get an element of F. So then the statement is that first D is linear. Second, D is injective. And third, D, if V is finite dimensional, then D is an isomorphism. So again, so the main idea is that if a vector space is finite dimensional, then there is a very natural way to think about this double dual weird space. This is just the same as V, and there is a very, very simple map which sends one to another. And later on I will show you a very nice example of that, which will be related to interpolation basis we discussed in homework 1. Importantly, if V is not finite dimensional, this map is linear and injective, but not surjective. And one can give an example of that. So let me do it. Okay, so proof. So D is linear, the first part. So this one is really easy, because if you take D of alpha 1 plus alpha 2 of any, d of v1 plus v2 of any function of phi is equal to phi of v1 plus v2, which by linearity is phi of v1 plus phi of v2, which is d of v1 plus d of v2. And similarly with multiplication on any element of the field. So D is indeed a linear map. So secondly, D is injective. So suppose d of v equals to 0 for any phi. So then what it means that d, so phi, for some vector v. So then it means that phi of vector v equals to 0 for any map phi from v to f. So if d of v equals to 0, it means every linear functional is equal to 0 on v. So why this cannot happen? Because it is really easy to write down a functional which does not have this property. So for that, so suppose v is not 0, then there exists a basis containing v. So this is just because every basis of a subspace, in particular the subspace generated by one vector, can be extended to a basis of the whole space. Notice that formally we proved this only for finite dimensional vector spaces, but I said that it is true in general. And then let phi be a map. Phi be a map from v to f, which sends any vector w to coordinate in front of v, so to speak, of v. So what we do, we take v, we write it in this basis, and we get something x times v plus where here we expand in the basis and expand in the basis. And this map just sends w to this coordinate in front of v. And we know that for every vector w there exists a unique way to write it down, so this is well-defined map, and this is linear, as we checked previous time. And then of course phi of v equals to 1, and we assume that phi of v equals to 0 for every phi, so we have a contradiction. And so phi is equal to 0. Perfect. So now we know that we have a map from v to v star star, which is injective and which is linear. So we just checked that the kernel is 0, right? And then, I mean, the part 3 is obvious, because we know that, so part 3 is, let me just prove it here. So we know that dimension of v star star, as we proved last time, is dimension of v star, which is dimension of v. And so we have an injective map between two vector spaces of the same dimension. So we know dimension of the kernel is 0, so dimension of the image by rank nullity is the same as dimension of v, so image is the whole space v. So this map is surjective. That's the proof. And then D is an isomorphism, because injective surjective linear map is an isomorphism. And remember, in general, if you have a finite dimensional vector space and you have a map to itself, if it is injective, it has to be surjective as well by this rank nullity result, and vice versa. So we have proven all the statements of the theorem, and we are done. So that's the end of the proof. Again, so one should think of it in the following way. So if you have a vector space V, there is this dual space. If you have the dual space to the dual space, it is again V. If a space is finite dimensional. If it is not finite dimensional, it might happen that this map is not surjective, and what it means you can come up with linear maps which you cannot obtain by just plugging in a vector inside your linear map. So this happens, and there are interesting results. For instance, if you have like vector space of all continuous functions or in segment, you have linear maps like plug in a point, or you have linear map like integration, and that all starts to be simple. So let me stop here with the proof of this theorem, and I want to discuss an example of a basis and a dual basis, which will be interesting example of that. Okay, example. So example number 3 in this topic. So let's take again the same vector space V as before. So we just take polynomials of degree less or equal than n. And we know that dimension of V is n plus 1. So it happens here that, of course, we have already seen a natural basis of V, which is just 1x and so on, x power n. But one can ask, okay, are there any interesting other bases? And there exists a very natural basis of V star. So let x1 up to xn plus 1 be some elements in F, which are distinct. So just all of them are distinct. So then let phi xi be a map from V to F, which just takes a polynomial and plugs in this point xi. So that's the most canonical, nice example of a linear map. Just plug in a point. And of course, since it's a map from V to F, this phi of xi is inside F star. Sorry, V star. And I claim that this phi x1 phi xn plus 1 is a basis of V star. So, I mean, the number equals to the dimension, so it's enough to prove that they are linearly independent or that they generate the whole space. So let's prove that they are linearly independent. So, indeed, they are linearly independent. So let's prove that. So suppose lambda 1 phi x1 plus plus lambda n plus 1 phi xn plus 1 equal to 0. So this is a map which takes a polynomial and sends it to lambda 1 p of x1 and so on, lambda n plus 1 p of x plus 1. So we know that it is true that it equals to 0 for every polynomial if we plug it in. So let's take, for I from 1 to n plus 1, so consider a polynomial pi, which just equals to the following thing. So it has here a product of x minus x1 times x minus xi is omitted. Remember this notation. Up to x minus xn plus 1 divided by xi minus x1 and so on, xi minus xn plus 1. So this we have already seen inside the problem about these polynomials, interpolation basis. And why this is interesting? Because phi xj of pi equals to 0 if I is not equal to j, and to 1 if I is equal to j. Simply because, like, imagine you plug in xj here, then you will get 0 if j is not I, because one of the brackets will vanish. And if you plug in xi, you will get actually denominator and denominator just being the same, and you will get 1. So we can plug in pi here, and if we know that 0 equals to this lambda 1 phi x1 plus of pi, And we know that all of them equal to 0 except one which equals to 1. So we get that lambda I is equal times 1 is equal to 0. So all these lambdas are equal to 0. And so these guys are linearly independent. So we have proven this that. And then since dimension of V equals n plus 1, we know that this is, it's a dual space to a space of dimension n plus 1, so it's n plus 1, so phi x1 up to phi xn plus 1 is a basis. Okay, so perfect. But in particular, what it means we can look at a dual basis. So remember, for every basis, you have a dual basis. So the question is, okay, what is a dual basis? What is a dual basis? And we know that a dual basis is, of course, a basis of V star star. But Plus theorem just tells you that there is a very nice map between V star star and V, where you take a polynomial, and to any functional on polynomials, you just plug in this polynomial. And so one can ask, what is a dual basis? And this will be, of course, some basis of V. And the answer is, of course, it is basis P1 up to Pn1 plus 1. So P1 up to Pn plus 1 is. And the reason is because, remember, for the dual basis, what you need to do, you need to take a vector in the dual basis, apply it to an element of our basis, and get 0 or 1 depending on whether numbers agree or not. And this is exactly what you do, because if you think about this phi xj of pi, this is nothing but d of pi applied to phi xj. If you think about it in the notation of the previous theorem, because what is d of pi? It's a map which takes any functional and plugs in a polynomial. And so in this way you get exactly the fact that d of pi and phi of xj, so d of pi, p1 up to d of pn plus 1, so these are elements inside v star star, is a dual basis. But again, so we can think of it as elements of our space V, just polynomials. And so in this way, we get that these guys form a basis as a space of polynomials. And this basis was discussed in the homework problem, and you hopefully solved it and wrote it down. So this is called interpolation basis. And then in general, there is this formula that if you have any vector V, then this vector V equals to E1 of V, E1 of V, plus and so on, plus En of V, En of V. This is just because, E1 of V, E1, E upper N of V, En. And this is just because these guys are nothing but coordinates of a vector V in our basis. But in this setting, it will just mean that a polynomial P equals to P of x1, P1, plus and so on, plus P of xn, Pn, where this P of x1 up to, xn plus 1. So these guys are polynomials, which form this interpolation basis. These are values of your P in these points, and P is a polynomial. So that's a quantity of polynomials, which you have seen in homework 1 problem. So that's the idea, and I understand that it's a little bit hard to follow, but a lot of important things in linear algebra come from this duality. In particular, you have already seen that there is some interesting business when you have a system of equations. You can look at space of solutions, or you can look at it as a kernel of linear map. If you have a matrix, you can look at rows and columns and do transposition. So all this stuff is related to this duality phenomena. So there are a few more things I want to say about dual spaces and duality, which are really interesting, but maybe slightly more advanced. Let me talk a little bit about that. Okay, let's look at more maybe advanced thing, how this duality phenomena explains systems of linear equations once again. So let's look at some most naive example. Let's take R3, for instance, and let's look at a system of equations say, I don't know, 2x plus 3y minus z equal to 0, and x minus y equal to 0, or something like that. So this is a system of two homogeneous equations in R3, and we know very well that here we talk about two planes, and they together determine a line passing through the origin, and space of solutions is a line. So we have a line. Okay. So what can we say about this line? So we have actually, inside R3, we have a subspace. So this is our space V, and we have a subspace W, which is this line. Perfect. So, okay, what are equations of this line? So, of course, if you have any point on the line, these two equations hold, but also you can add them up. For instance, equation like 3x minus plus 2y minus z equal to 0 also holds. So actually, there are lots of different linear equations which are true for every point of W. So how to think about it? So what is a linear equation? So let's consider a map phi1 from R3 to R, sending x, y, z to this 2x plus 3y minus z linear combination. So this is definitely a linear map. So phi1 is an element inside V star. That's just because, you know, I mean, it's canonically like very classical example of a linear map. And then we can take phi2, which is another linear map R3 to R, and this phi2 sends x, y, z to x minus y. And this is also a linear map, and basically what we have here, so the system of equations is a system of equations saying that phi1 of v equal to 0, phi2 of v equal to 0. When we think of vectors x, y, z inside R3 as vectors. Perfect. So W is the space of solutions of this system of linear equations. So in particular, this is true just because we know by linearity of linear maps that if phi1 of v equal to 0, phi2 of v equal to 0, then phi1 plus phi2 of v also equals to 0. So that's just because you can add phi's. Perfect. So what this tells us? So this tells us that basically if you have the system of equations, you can think of its solutions as a linear subspace of this R3, and equations themselves are basically such linear maps which vanish for every element in V. So now we come to this general picture. So definition. So let's suppose V is a vector space, and W is a subspace of V. Subspace. Then define W perp. It's called orthogonal complement or dual subspace, maybe properly. This is a subspace of V star. So this is a subspace of dual space, and this consists of alpha inside V star such that for every V in this W, alpha of V equal to 0. So basically, you can think if V star are linear maps, so this is literally linear maps vanishing on V, or you can think of it as basically each of them gives you an equation, so you can think of it a little bit unofficially as equations, vanishing on W, equations for W. So this is a notion of this dual space inside V star. And then this is very, very important. So basically this explains to us that if you have a system of equations, you can think of it as a bunch of elements of this dual space, and you are trying to find actually what is the orthogonal complement to it. So you're trying to recover W by this W perp. So then let me formulate a main theorem about that. So theorem. So first statement is that dimension of W plus dimension of W perp equal to dimension of V. Of course, it is some form of rank nullity theorem, so nothing else, but still that's kind of very important. And in particular, it tells us that if you want to know how many solutions this system of equations has, you need to take this equations and see what is the dimension of the subspace they generate in the space of all linear equations. So this is kind of tells you the relation between equations and solutions. And then there is another statement. So yeah, we assume here, so V is finite dimensional. So of course we can take this W perp, and then we can take W perp perp. And of course it is a subspace of V star star. But we know that V star star is isomorphic to V, and there is this very nice linear map D, which we discussed already. So we can literally think of V star star as V. And so we can think of it what it is inside V. And of course, so basically under the map D, so this is isomorphic to W via this map D. So basically, this duality is symmetric. So you can think of linear equations determining a subspace, but you can think of subspace determining all linear equations which is satisfied on that. And this becomes a correspondence between these subspaces. So maybe let me say 3. So if you have a V and V star, and you have this W goes to W perp, is a bijection between subspaces of V and V star. So that's very important. So basically the idea is that you can look at all possible systems of equations. For each of them you can look at space of solutions. Or you can take all possible spaces of solutions, so subspaces inside V, and look at all equations they satisfy. And this gives a bijection between all subspaces of V and all subspaces of V star. So basically, there is no difference between thinking of equation as kind of equations for V, or thinking of when you have V, you're trying to find all equations which are true on V, and this is kind of the same thing, sort of. So so that's very important theorem, and let me prove that. The proof is not terribly hard, but what is important is to understand it. Also, what you can see here is if you have W1 contained inside W2, then W2 perp will contain W1 perp, because what this says, it says every vector in W2 is inside W1, and then of course every equation which is satisfied for W1 will be also true on W2. So this bijection, it kind of reverses inclusions. So that's very interesting setting. Perfect. So let me prove the theorem. The proof is just an exercise in linear algebra, which we already know. So let's prove it. So proof is not hard. So proof. Proof is not hard, and actually it is very close to this proof in homework where we had a hyperplane and we were trying to prove that it is given by one equation exactly. So in a sense, this is exactly what the theorem tells you, because what it tells you is that if you have a hyperplane inside V, then the dual space will be something inside V star, and actually maybe that's a good remark. So if you take hyperplane here, so if this is a hyperplane, for instance, then the dual one will be a line, because we know that dimensions are, if this is n-1, this is 1. But what it actually means, if you take a hyperplane inside of V, then if you look at all equations which are true, and it will be exactly one line, so one equation up to rescaling. So this is exactly problem from homework, basically. So let me maybe, before proving it, let me say that. So example is from homework. So if you take V and inside you take a hyperplane, this is W, or maybe, yeah, W. So then you can look at, so there exists an equation a1x1 plus tdd plus anxn equal to 0, which holds if and only if vector x1 up to xn is inside W. But of course, this equation, if you think of it, so what this equation is, you can just think of a vector phi1, which is just this linear map sending x1 xn to a1 x1 plus and so on plus a and xn. This is a linear map, and phi of v equals to 0 if and only if v is inside W. And what it means that if you take the orthogonal complement, so this W perp, this is of course, we look at all linear maps which vanish for every element in the hyperplane, but this will be just this one or this one times the constant. So this is just lambda phi for lambda in F. And so this is nothing but the span of phi, so this is a span of phi. And so this is a line. This is a line. Perfect. So that's the duality between hyperplanes and lines. I think it's kind of cool, actually. Okay, so proof of this theorem, part 1. So let me start with part 1. So part 1 is really not very hard. So choose a basis E1 up to EK of W and extend it to EK plus 1 to the D, so that E1 up to En is a basis of V. Basis of V. So we have W, we have this basis, we have this V, and then of course, basically, if you think about vectors x1, xn is inside W, if and only if x k plus 1 equal to equal xn equal to 0. So basically, you think of this W as the space of solutions of this very boring system of linear equations. But then, of course, we can look at W perp. So let E1 up to En be the dual basis. And then, of course, what this means, it means that then EK plus 1 and so on En are inside W perp, because these coordinates are, because xi is nothing but EI of V, of the vector x1 up to xn. So of course, when I choose a basis, I can write my vectors as this, just tuples of elements. Perfect. So this just means that I have already n minus k vectors in W perp, and they form a part of a dual basis. So dimension of W perp is at least k plus n minus k. And then okay, so let's suppose some phi inside V star is in W perp. So then we know that this phi of E1 equals and so on equals phi of EK equal to 0, because that's a basis of our W. But then so if phi is equal to A1 E1 plus plus A n En, then we know that, so we can write any linear map in a dual basis, but then we know that if we start plugging in E1 up to EK, we get 0, so actually A1 equals to DD equals to AK equal to 0. So then it means that W_perp is inside the span of this vectors EK plus 1 up to En. And so what it means is actually this is an equality, because we just proved that all these vectors are there and it is inside the span, so this is an equality. And so dimension of W_perp equals N minus K. And that's the proof of the first part. And honestly, second part absolutely follows from here. Let me erase this part and I will explain it there. Okay, so perfect. So so we have proven 1, and then 2. So if you just take this, just using this idea. So if you take W_perp, so this should be inside. So we can think of it inside V star star, which is just V. We can identify them, and again, so if you just look at it, I mean, what is a vector there? So we know already that W_perp, so we take this span of EK plus 1 and so on En perp, and definitely it has vectors E1 and so on EK are there. So so that's just because if you take any vector E1, so because for instance, D of E1, if you take this D of E1 inside V star star and plug it in inside E, say K plus 1, you will get nothing but, according to this formula, so you will get, sorry, EK plus 1, you will have to take EK plus 1 of E1, which is the K plus first coordinate of E1, which is just 0, and so on. So you just see that if you take any of these elements of the dual space, plug in this EI, so you get 0, and so what it means that W, which is the span of these vectors, is inside W_perp. But then, of course, we know that dimension of W_perp is N minus dimension of W_perp, but this is N minus dimension of W, which is just dimension of W. So, and we have already K vectors there, which are linearly independent, and so we see that W equals to W_perp. So that's kind of, and you should have an example in mind that you sort of look at three-dimensional space. You have line, you have orthogonal plane. That's all related to orthogonality, but we will talk about it later. You have kind of line, orthogonal plane, and if you take a line orthogonal to a plane, you get your line back. So that's kind of idea. Cool. And 3 is obvious from here because basically it means that if you have, so this is part 2, and then if you want to prove it's part 2. If you want to prove part 3, then basically you have this W_perp, and then you have, so this is a map in one direction, but in the other you can take W_perp, which is sorry, you can take any subspace, let's say W prime here, and send it to W prime perp. And then if you take W, you go to W perp, then you plug it in here, you get W inside. But if you instead start with something here, you go to perp, you get perp back, and this is again the same space. So this is just means that you have a map, and the same kind of map, just the same perp, is an inverse map. And so when you have two maps which are inverse of each other, you have a bijection. So so this map which takes a subspace to this perp thing has an inverse, and so is a bijection. So basically, again, if you have a vector space, you have like points, lines, planes, dimension 3 subspace, and so on. And the duality tells you, okay, lines are dual to hyperplanes. Planes are dual to subspaces of dimension -2. Up to hyperplanes are dual to lines. And the whole vector space, of course, is dual to 0 subspace, because if you take like here W equal to V, then you are looking at all linear maps which vanish on every vector in V, which is just 0 map. And if you take 0, you are looking at all linear maps which vanish on 0, which is just the whole space. So in this way, you have this sort of correspondence between subspaces of V and subspace of V star, which takes dimension to dimension n minus dimension. Okay, so this is really hard, I know that, but this geometric kind of correspondence is inside the heart of linear algebra. And again, all the fact that we were able to think about matrix rows and columns, their dimensions are the same, or we were able to talk about these transposed matrices and so on and so forth, that all comes from this duality theorem. Okay, so thank you very much. Let's end here.